China. And I'm very glad here to introduce our work about using an in-kernel library to improve the functionality and performance of eBPF-based network functions. And the work of eNetSTL is a joint work with the Hong Kong University of Science and Technology and Peking University. Now let's get started. We first introduce the background of our work. In today's network, implementing network functions using eBPF have become a trend. On one hand, eBPF-based network functions are widely deployed in production by well-known companies, including the Meta, Google Cloud, and Cloudflare. For example, Meta put eBPF into production at scale with its load balancer project Chen. And beyond that, there are many research and open source projects implementing network functions based on eBPF. Examples including the Polycube and Slim project and the literatures we list on the right side. So such trend can be attributed to the advantage of eBPF, and as an emerging kernel extension technology, eBPF allows us to safely run custom code within the kernel and does not any kernel modifications. And the eBPF-based network functions are typically attached into the XDP hook or the TC hook in the form of eBPF programs. And the advantages of eBPF-based networking include first, and eBPF can integrate well with existing cloud ecosystem, enhancing the intra-host kernel communication. And secondly, the eBPF supports a high-performance packet processing without saturating the CPU and enhance the CPU's efficiency. And finally, the safety and no intrusion into the kernel of the eBPF enhance the maintainability and flexibility, and also enables fast development and deployment of network functions. So, given the advantages of eBPF, we follow the trend and try to implement 35 network functions using eBPF. And we attempt to implement their core operations of these 35 network functions using eBPF. However, we encountered two problems. First, the incomplete functionalities. It is unable to implement 3 of them due to the inherent programming limitations of eBPF. For example, we can implement the skip list-based key value store due to the lack of non-contiguous memory support in eBPF. And secondly, performance degradation. While 28 operations can be implemented using eBPF, they suffer from significant performance degradation due to the lack of advanced instructions in eBPF ISA and other safety mechanisms, for example, the locking and costly helper functions. For example, due to the lack of the SIMD instruction, countermean sketching has a performance degradation reaching up to 49.2%. To solve these two problems, currently there are two potential solutions. First, we can modify the overall architecture of the eBPF, including expanding the eBPF ISA, modifying the JET compiler, verifier, and so on. But this requires deep changes to the kernel, making it hard to deploy quickly and meet the urgent needs of the community. And secondly, we can implementing all problematic network functions within the kernel. However, integrating all network functions into the kernel may require deep changes to the kernel. And per network function, per kernel module approach may raise the new issues of maintainability and safety as we should take care of numerous kernel modules. So in short, both the solutions undermines the core benefits of eBPF, its efficiency and flexibility, and is impractical. This motivates our work, and we ask, can we achieve a comprehensive functionality and high performance for eBPF-based network functions without compromising the eBPF advantage of flexibility and low intrusion? And to answer this question, we first dive into the 35 network functions first. We observed that network functions usually share similar behaviors. For example, and both the countermean sketch and the heavy keeper share the behavior of calculating multiple hash functions. They both compute multiple hash based on the packet header and use these results to locate the counters. After that, the two network functions may perform different actions on the counters. We further dive into the design of the 35 representative work and observe that they share 6 similar behaviors. We conclude them as follows. First, the fast locating using the bitscan instruction. For example, we can use the FF's instruction to implement the priority queue. And second, fast hash computing using the SIMD. And third, we may build on the fundamental data structures such as the min heap and list buckets. And fourth, network functions may use the random update to reduce the per packet overhead. And fifth, we may use the non-contiguous memory to organize the data structure. And finally, network functions may arrange multiple packets in a contiguous memory for fast key comparing. For example, the Google hash. And due to the space limitation, please check our paper for more details of these behaviors. Next, we perform a quantitative analysis on those behaviors and find that they are performance critical, accounting for 20.6% to 65.4% of the overall performance of network functions. So, based on the above observation, our core idea is by supporting these 6 behaviors in one standard library, we can enable high-performance eBPF implementation of existing network functions and benefits the future ones as well. Here, we introduce the eNetSTL, the standard in-kernel library for eBPF-based network functions. And eNetSTL is designed to be spatial minimal, minimizing the intrusion into the kernel, and temporarily stable, maintaining the flexibility of eBPF and the stability of the kernel. The eNetSTL contains 1 memory wrapper, 3 algorithms, and 2 data structures, which coverage the 6 behavior we mentioned above. eNetSTL is a kernel module, and eBPF programs interact with eNetSTL through APIs, and these APIs are implemented as the BPF kernel functions, which we call it the BPF Funct. And the relationship between the eNetSTL for eBPF-based network function is just like the relationship between the C++ STL for the C++ applications, and this is the reason we call it the eNetSTL. The design of the eNetSTL should address 3 design challenges, and we will describe them later. The first challenge is how to support the non-contiguous memory without compromising the safety. And we solve this by introducing a pros-based memory wrapper with a lazy safety check. Initially, the challenge of supporting non-contiguous memory in eBPF lies in not supporting unpredictable lengths and persistent storage simultaneously. For example, in eBPF, we usually persist the memory in BPF maps. However, the BPF map only supports a fixed number of entries. To address this limitation, we use a pros-based method, introducing a pros data structure to manage the ownership of all dynamically allocated memories. Upon the memory allocation through the alloc API, its ownership is transferred to the proxy, which means that the proxy will hold the reference count of the memory blocks. And we purchased this pros data structure with only 1 instance in the BPF map to overcome the above limitation. And next, to avoid the circular reference, we decouple the relationship and ownership. We establish the relationship between the 2 memory blocks with the node connect API. And this API is just do the job like that A point next equals B. And the decouple of relationship and relation and the ownership means that the A does not hold the reference count of B, and that not hold the ownership of B. And although promising, this method will introduce a new issue of use after free. For example, and we should avoid dereferencing A point next when the B is released. And to address this issue with a low overhead, we introduce a lazy safety check mechanism. We delay the safety check until the memory release phase to eliminate the need of every safety check in the getNext API. And this is built on our observation that for network functions, the memory traversing is more frequent than the memory connect and release. And we achieve this by record every memory relationship when the memory blocks are connected, and when the memory blocks are released, eNetSTL will automatically delete all the invalid relationship. The second challenge is how to minimize the interaction overhead between the eNetSTL and the eBPF. Well, the interaction overhead between the eNetSTL and eBPF while preserving the generality, and we solve this. We solve this with designing the interface with carefully balanced generality. We take one algorithm in eNetSTL for an example, and this algorithm is designed for supporting multiple hash computing. To enable that, the most general way is to design the APIs in an instruction level, which we object a single SIMD instruction as a single function, and we build the multiple hash computing by calling such APIs in multiple times. However, this approach introduces significant interaction overhead due to the memory loads and stores, because for each SIMD instruction API, we all need to load the parameter from the memory to the SIMD specific registers, because the eBPF ISA does not support the SIMD. Next, another option is that we can use a low-level algorithm abstraction. For example, we can utilize a low-level interface that takes a key, that is the packet header, as an input, and perform calculations with multiple hash functions, and finally copies these results back to the output memory. However, this still introduces a significant overhead because the results of the multiple hash is too large to directly returned by registers, and eBPF cannot directly access the results temporarily stored in the SIMD register. Finally, eNetSTL provides a high-level interface that encapsulates multiple hash calculations and subsequent post-operation within a single algorithm. This method is feasible with our observation that network functions usually rely more on how to utilize the result rather than the values itself. For example, for the column sketch, which use the multiple hash to locate the counters and increment the counter. Such counting is the post action, and we call it the hash plus counting. The third challenge is how to mitigate the safety risks of eNetSTL itself, and our solution is combine the Rust, eBPF verifier, and manually code reviewing to improve the safety of eNetSTL. From the start, we implement individual components in eNetSTL using the Save Rust to ensure the safety of the individual APIs. Next, we manually review a small portion of unsafe code. This unsafe code is necessary because the unsafe Rust or the C is needed for interaction with the kernel. And we adopt the practice of safe abstraction by isolating the safe and unsafe code. While ensuring the safety of individual APIs guarantees the safe termination of the entire eBPF program, it does not fully address the memory safety due to the different memory model of between eBPF and Rust. For example, the eBPF program must call the alloc APIs and the release APIs in pairs rather than the III-based method used in Rust. Last, therefore, we further ensure the safe interaction between the eBPF and eNetSTL for the memory safety. Specifically, we ensure that the eBPF program adhere the correct API usage. For example, we ensure that eBPF programs should call the alloc and release API in pair and prevent the out-of-bound memory access. We achieve this by using the BPF kernel pointers kptr and BPF kernel functions kfunct technology, which provide the metadata to the eBPF verifier framework for custom verification. For example, we can annotate the API parameter to avoid the outbound access, and we can annotate the two APIs to enforce such paired calls. Here, we show an example of implementing countermeasure sketch using eNetSTL. First, we should define the memory layout of the countermeasure sketch and use a BPF map to handle the instance of the memory of countermeasure sketch. Secondly, compared to the pure BPF version, which calls the hash function sequentially. The eNetSTL version calls the parallel API provided by the library, and this library is a Kfunct. Using Kfunct in eBPF program is just like use helper functions. We implement eNetSTL as a single lightweight kernel module and without any kernel modifications. All the source codes of eNetSTL and use cases have been open sourced in GitHub. For evaluation, we use 2 servers, and each one equipped with a dual-port Intel XL710 NIC. One server is used as the traffic generator, and the other one is the device under test where we deploy the network functions. We report the single-core performance by disabling the RSS and RPS. We evaluate 8 network functions with their core components implemented with the pure eBPF, the in-kernel one, and the eNetSTL. Now let's check the throughput result. First, you should know that we show that eNetSTL achieved the goal of functionality by enabling the skipped-based key-value store in eBPF. As shown in the figure, compared to the eBPF, eNetSTL can achieve up to 1.8 times performance improvement. Compared to the kernel modules, the eNetSTL has a gap less than 8%. The above results demonstrates that eNetSTL achieved the goal of high performance. For latencies, we find that eNetSTL does not increase the end-to-end latency of network functions. This is because the eNetSTL improved the throughput by speed up the processing of individual packets instead of using benching. As we all know that bench could increase the delay of the packets received earlier. Now at last, we make a conclusion. In this paper, in this work, we identify 2 problems with incomplete functionality and performance degradation in the 35 representative network functions using eBPF, and we introduced the eNetSTL and practical in-kernel library for high-performance eBPF-based network functions. And thank you for your watching and listening. Please contact me for more details. If you have any question.